Recall, the fundamental theorem of calculus states that the definite integral from a to b of f of x dx, if f is a nice continuous function, is given by big F of b minus big F of a, where big F is just an antiderivative of little f. That is, the derivative of big F is little f. What I want to do in this video is two things. First of all, I want to talk about how this helps us to make sense of the mean value theorem, and then second of all, how the mean value theorem can help us prove this. So let's go back and remind ourselves of the mean value theorem. There were two different results that were both called the mean value theorem. One version of the mean value theorem, the first one we saw, was the mean value theorem for thinking about derivatives. When you have some function, y equals f of x, what this first version of the mean value theorem said is if you found the average rate of change from, say, time a to time b, or whatever the variable here represents, from a to b, that average rate of change, f of b minus f of a all over b minus a, is equal to the instantaneous rate of change for some value c between a and b. That is, f prime of c is equal to f of b minus f of a all over b minus a. So that was the first version of the mean value theorem. Then we saw a second version that said if you have some area, so now I'm thinking about the area under this graph from a to b. So I'm thinking about the area under this graph. Well, the area under that graph is given by the definite integral a to b of f of x dx. And then if I divide that area by the width, by 1 over b minus a, we get the average height of this function. So there's some special height here. Not the highest height, not the lowest, somewhere in the middle, some special height h, some average height h, such that this area, h times the width b minus h, so this h times the width b minus a would come out to give you the same as the area under the graph of f of x. But that height h is itself equal to the height of the function at some value c. So I can replace this h by just saying that is going to be the height of my function. That's going to be f of c for some value c between a and b. And we called both of those the mean value theorem. Both of these were called the mean value theorem. And at the time, maybe it didn't make sense why we're using the same name, mean value theorem, for both statements. But now, in light of the fundamental theorem of calculus, I claim it should make sense. Why? Because we can now rewrite the statement. The definite integral from a to b of f of x dx is the same thing as just big F of b minus big F of a, and then we're dividing that by b minus a. And what the second version of the mean value theorem is telling us is it's saying somewhere that's little f of c. But little f is the derivative of big F, so that's just big F of c. And notice we've now translated the fundamental theorem of calculus. Let's just translate this mean value theorem talking about the average height, the average value of a function, into the mean value theorem from before. This is exactly the same as before. You're talking about the antiderivative now. It's the mean value theorem for the antiderivative. So the fundamental theorem of calculus let us change these two statements to be an equivalent statement. Here it's a statement about your instantaneous rate of change equaling your average rate of change. Here it's the same thing but for the antiderivative, which translates into the statement about your average height. So now hopefully you can see how these two statements of the mean value theorem really are being justified and being called the same thing. So that's why we call them both the mean value theorem. Even though one is about slopes, and 1 is about area. So what the fundamental theorem of calculus is doing is it's building bridges between very different ideas about instantaneous rate of change, ideas about area, and it's showing us how those two ideas are actually related to one another. Okay, so hopefully this helps conceptually for you to organize in your mind why the mean value theorem has two different versions that look different, but now you can see they're actually saying the same thing. They have the same form to them. The second thing I want to do now in this video is I want to try to justify why the fundamental theorem of calculus is true. Like, why should you believe this? This is a fundamental theorem of calculus. But why should you believe this? And I want to give you an argument for this using just the mean value theorem. So while this helps us make sense of the mean value theorem, we proved the mean value theorem. I gave you an argument for this, which itself used the intermediate value theorem, just used properties of continuous functions. So we're going to use this mean value theorem to help us see why this is true. So let me show you how we do that. Okay, here's the setup. I want to show that f of b minus f of a is the same thing as this definite integral. So here's how we're going to do that. Let's think about f of b minus f of a. And it always helps to draw a picture. So let me draw a little picture here. Let's draw, whatever our graph looks like. Maybe we draw the graph to look like this. Generic graph, y equals f of x. And we're thinking of it as going from some point A to some point B. And what I'm going to do is I'm going to divide this into rectangles, right? I always divide this into rectangles, and I divide into rectangles by dividing this interval into n little widths. So these are going to make the right endpoints of these rectangles. And you can think of these as being just like the points x1 here, x2, all the way through. The last one is xn, where xn just happens to correspond to my b, right? Now, typically when we draw rectangles, we do right endpoint rectangles. You could also do left endpoint rectangles. It really doesn't matter where the rectangles touch in the limit. And so what I'm going to do to introduce a name for A is I'm just going to introduce one more guy here called x0. I'm just going to call him x0. So now I've divided this up, this interval. I've labeled points x0 through xn, representing the n widths that will comprise my rectangles. So here I'll have, my various rectangles at each one of these. Okay. Here's the next step of the argument. Big F of b minus big F of a, using the language of x's, I can just think of as big F of xn minus big F of x0 minus big F of x0. But you may have noticed I left some room in between, because what I'm going to do now is I'm going to fill in some extra stuff into this equation. Here I'm going to put an extra line, big F of xn minus 1. I can't just add an extra minus here. So if I'm subtracting this term, I have to add it back. Big F of xn minus 1. So I'm subtracting and adding that term. So those secretly are going to be canceling each other. But I'm building a structure here. So just stay tuned, see what's going on. Now I'm going to have a big F of xn minus 2. And then I'll add it back in plus big F of xn minus 2. So I haven't changed anything because we know secretly these will cancel. But you keep doing this. Then you do big F of xn minus 3, and then plus big F of xn minus 3, and so on and so forth. So those would secretly cancel. I'm not going to draw it, but that's what would happen. And you keep going until you get to big F of x2 minus big F of x1 plus big F of x1 all the way down to big F of x0. And so there's this nice, it's called telescoping property, where these guys just cancel with each other, so that all you're left with is the first one and the second one, but xn is the same thing as b, and x0 is the same thing as a. Okay, so all I did here was stylistic, and you might think this was a completely pointless step. It seems pointless until we go back and we remember the mean value theorem. The mean value theorem. Because what does the mean value theorem tells me? The mean value theorem tells me that big F of, say, b minus a is secretly equal to f prime of c times some number in between times b minus a, where c is some number in between b and a. So like here, just remember, this c is some number in between b and a. In exactly analogous way, big F of xn minus big F of xn minus 1 will be the same thing as big F prime. This is the same thing as big F prime of some value c, I'll call it Cn, where Cn is some value between those. So let me just put this as like some Cn is some number between xn minus 1 and xn. And this continues. Your second line, well, it's not, it's that times the b minus a. So I shouldn't forget the b minus a. And then this next line right here, so let me do this all together. This next line right here is the same thing as just big F prime of Cn minus 1, where that's just going to be some number between these two. You know, some number between here and here is your Cn minus 1, is your Cn minus 1, times that by b minus a. And so forth and so on. Until here on bottom, this is just some big F prime of some C1, where C1 is just some number between x0 and C1. C1 is some number between x0 and C1 times b minus a, times b minus a. And you know, up here, between x1 and x2, this is the same thing as just f prime of some C2 times b minus a. Okay, so this is getting a little bit messy, but let's just clean this up now. All of these have a times b minus a piece, so pull out that b minus a. And then, it's not actually times b minus a. I made a mistake here. If it was b and a, it would be b minus a, but this is the distance from xn to xn minus 1. And each of these widths are not b minus a. Each of these guys have width b minus a divided by n. So each of these should actually be b minus a divided by n, b minus a divided by n, b minus a divided by n. So factor out that b minus a over n, and you're left with the sum of big F prime of some ci, where I goes from 1 to n. But what is F prime? F prime is just little f. So we can come back here and change that F prime, all of those F primes, the same thing as just little f. And so that's just saying width times the sum of f times c1, c2, c3, where each of these is just some little point in this interval. That means f of c1 is just the height of the rectangle that touches this guy at height c1. It's just the height of this rectangle. So f of c1 times b minus a over n just gives you the area of this rectangle. And f of c2 times ba minus n is just the height of this rectangle. And so forth and so on. Each of these is the height of the corresponding rectangle. So these are not right endpoint rectangles. The C is somewhere in the middle of the rectangle, but in the limit, you still have, you take the limit of this as n goes to infinity, if we've broken this up with more and more and more n, of larger and larger and larger n, this is still converging to, that's still approaching this value right here. And so we get f of b minus f of a equals this. And we can do this for more and more n, take the limit as n goes to infinity, and sure enough, it's equal to your definite integral. So kind of a tricky proof here. This is a little bit abstract, but hopefully this helps to give you some justification how just using the mean value theorem, we're able to prove the fundamental theorem of calculus.